Cool. Thank you, everyone, for being here, and thank you to the Antithesis team for organizing tonight's event. This is one of those talks where I have more questions than I have answers. So if you're here looking for like, here's how to do this or here's how to do that, I can't help you. We just heard from like two of the probably most experienced people you could talk to on deterministic simulation testing and property testing and these sorts of techniques. I will be discussing these techniques, but in a slightly different context. At Chroma, we build a search engine for AI applications. So what that concretely means is language models that don't have access to offline data, private data, or real-time data that they didn't see when they were trained. We give developers the ability to inject that data into the context of the model so that they can then perform whatever downstream task they need to perform. And we kind of sit in between building a very low-level and complicated distributed system, but our customers are people building with machine learning. And so I've been reflecting a lot on this dichotomy and how we view reliability as systems builders and how people building LLM applications view reliability. And what I want to talk about today is system engineers have always had to live with unreliability. Networks crash, or networks split, machines crash, drives get corrupted. Sometimes you get a solar flare and it literally makes S3 flip a bit. This actually happens. And what I'd like to kind of posit is that the tools that we use as systems builders and as distributed systems builders to make our systems reliable could potentially be useful in this other domain of LLMs. LLMs are just another unreliable, non-deterministic component in your software stack. They're just a function. You just call them, and they take some input, and they produce some output. We don't need to make them more complicated than that. We don't need to view them as AGI or ASI in order to make them productive and useful. And I think that when you take that lens, you can start to ask the question of how can we build reliable applications using language models, using techniques that many of you know far more about than I. So what I'd like to do is maybe just invite some speculation on how these techniques could be fruitful for this domain, and maybe have you walk away maybe in 6 months with a thought on how to contribute back to this effort on how do we make LLM applications reliable. So with that, I just want to talk a little bit about the concrete topologies that LLM applications can take, just so we can ground our conversation. So this diagram is very shamelessly ripped from Anthropic. We have some Anthropic people in the room, so I want to call that out. But if you kind of view a couple different topologies of applications, the way language model applications get built, the most simple is like what we were all doing 2 years ago, right? You just view it as some natural language function. So take some input, take some output. Maybe you ask the question, what is the capital of France? And it says the answer. And then the second way of viewing this is as a workflow. So now you just don't have a single model call. You're composing a model call into some sort of workflow. So you take some input. Maybe you have some model that does one subtask, another model that does some other task, and you've kind of prompted these models to do specific and narrow purposeful tasks. So you're really just composing these single functions in a human-defined workflow. And you're taking kind of your domain knowledge and encoding it in program execution. This is how we all are used to writing programs. The last one is kind of the new thing, and if you've used Claude Code or Codex or OpenCode, these sort of like agentic coding tools in your CLI, if you haven't, you should try them out. They're very, very helpful. They present a sort of third alternative way of looking at how to build LLM applications, which is you have some model, you give it some set of tools, and this performs agentically, meaning autonomously in the environment or with human intervention when required, a set of tasks. And it decides what to do on its own. It interacts with the environment. If it's a coding agent, the environment is the code base. And then it goes forward, making progress on its task. But the central thing that ties all these things together is we're stitching a bunch of language models together, and we're trying to produce a system that's reliable. We're trying to produce a system that has a high pass rate at the task at hand. Or an alternative way of looking at this is we're trying to produce a system that has the lowest number of interventions per token, right? As the system proceeds, as the system progresses in its execution, you really don't want to have to intervene, and you want to reduce the amount of times a human has to step in and tell the coding agent or the law assistant agent or whatever the domain may be that you're doing something wrong and you need to correct it. And I'd argue that if we want to make AI systems economically productive, this is really long-term what you're maximizing. And for a long time, this was what self-driving, or to still self-driving is maximizing, right? The number of human interventions per mile is sort of the agentic metric for self-driving cars, and we can kind of think about an agentic metric for AI systems. And there's a lot of work in this direction from the machine learning point of view. So I'm not going to actually talk about any of that. I'm almost like willfully ignoring it. And I'm only going to make kind of hand-wavy analogies to a lot of the topics we've heard today. because I think they're fruitful. I think it's fruitful to view some of the techniques that we heard in the previous two talks in the lens of how to build reliable LLM applications. And I think it's important to maybe talk about what reliability actually is. This is one definition. If you want like the textbook definition, right, here's your math. The reliability of system is the probability that it's up, which is the integral over the PDF over time, all the way to infinity. So what does this actually look like? This is the task that someone on our team, Robert, actually, if you want to go talk to him after, has been running through models for like a few years now, where like every few months a new model generation comes out. We just try it as a toy task. So let me tell you about this task. We tell the model you're an email processing agent, and you just have to output the priority. So tell me if this email is low, medium, or high. Very simple. We give it 4 rules. Rule number 1, Alice is high priority. These are in natural language, so we're not like symbolically encoding them or anything like that. Rule number 2, Bob is low priority. Simple. Rule number 3, Charlie is medium priority. Rule number 4, Alice is normally high priority, but she's out of office, so let's just mark it down. I don't want to bother her while she's out of office. I'll get back to that when she's in town. And then I say, here's an email. Please tell me the priority and the requested output. I want this JSON. Email is from Alice to me. Subject, lol, the building is on fire. We're on fire. What should we do? I don't know, maybe we're like both basketball fans and our team's really doing well or something. So if you give this to a wide variety of models, under seemingly nonsense perturbations, the model will sometimes succeed and sometimes fail, and it'll also think for times that will make you squint and go, are these things actually smart? So it said, the priority is high, but I'm very clear in my rules-based system, the priority should not be high. Alice is out of office, and there's this temporal constraint. So this is an example failure that, and I can show you all the countless runs we've been doing for a while now, or if you just like take this prompt and you put it in, and if you like remove the spacing, the output will change. If you perturb a few words, the output will change, and it's very hard to know why, right? And if you start to squint, you start to go, oh, this sounds a little bit like property testing. It sounds a little bit like these other techniques that we've started to hear. And the reason that it sounds like that is because these domains all suffer from the test oracle problem, right? This should be no surprise to people in either of these domains, machine learning or distributed systems, but we don't have a system that tells us what the answer is. This is canonically known as the test oracle problem. And you might say, hey, Hammad, but we have evals, so we're good, right? And I would say, not really. These are really good if you're training a model, but it's like debugging. You can't really debug an eval. It doesn't tell you why it's failing, how it's failing, where it's failing. It doesn't tell you what to do after. It's like if I dropped you into your test suite and I just said, cool, it failed. And you're like, what test, right? What line? It doesn't tell you anything. And so I don't think it's that helpful. And as software engineers, we know that there's a difference between a good test and a bad test, a representative example-based test, or a good unit test, or a good integration test. So you can't just say, oh, I made an eval, and so therefore this eval must be good. You have to be rigorous about what that evaluation is actually doing. And so the question I want to posit is how can we apply learnings and intuitions from these other domains, of which, again, many of you and the people who spoke before me know vastly more than I do, but how can we apply those intuitions to this domain? And the thing that stands out to me is, has anyone seen these 2 papers by any chance? Cool. Yeah, so these are the papers that for me clicked, and I was like, oh, these are really useful primitives in distributed systems. So the title of the papers are generally to do with formal and semi-formal methods, right? Which are, how can you sort of formally specify your system, or in a lightweight way specify the model of your system so that we can do more advanced testing against it, like simulation-based testing or property-based testing. And if you're building distributed systems that scale and you're not doing this, or if you're building data management systems and you're not doing this, you have bugs and you don't know. You absolutely have to be doing these things. And these are widely adopted. AWS, GCP, everyone who's serious about building data infrastructure is using these techniques. And I think that we can leverage these techniques, specifically property-based testing and model checking. I think that these are 2 very, very useful techniques. So just by show of hands, how many, I know we covered it once, but just by show of hands, how many people think they understand what property-based testing is? Okay, we still have some confusion. World's shortest introduction to property-based testing. Imagine I have a string. Imagine I have a function that reverses this string. If I do f inverse of f of x, so I reverse this function that reverses the string, I should get the string back out, right? Now I can generate inputs at random, and I have this property that the input should always be equal to the output. That's property-based testing in a nutshell. You want to assert invariants to your system because you don't have some oracle that tells you this is what you should be doing. So instead, you want to ask the question, what should always be true? And that kind of reframes how you think about testing. And you might be saying, well, how does that apply to language models? Right? We can't like randomly generate the inputs. What would that even mean? And so we did a little bit of research earlier this year, and we showed that you can. If you have some language model-based system, you can actually take data, you can feed it to a language model, give it context about the task, and you can have it generate respective queries. And this works. We show that actually the data sets that you end up generating end up being in distribution, but also representative of data that is outside of your core data set. And you can go read this report. It's written by Kelly on our team, who led the research here. And really, we think that this is the first step in unlocking the ability to give programmers and software engineers a more robust way of debugging model-based systems. So just to recap, what we're doing is you take your data, which is the chunks, you give it to the language model. We then filter these chunks into ones that we think are representative of the data set. We use them to generate queries, and then we sort of condition the query generation with some example bank of queries that know about the domain. And we show that the data set is actually representative, which is really important if you want to do some sort of fuzzing of the input space. So the analogy is you can now think of property testing by a different name, which is generative benchmarking, which is what we called it in the paper. Now you can start to ask, well, what are invariants that I can uphold about my system, right? So let's say I'm building some sort of financial analysis agent or language model-based application, whatever buzzword you'd like to choose. And you give it some financial records, and you give it this financial record generator, and that's just that benchmark thing that I showed you in the last slide, right? It just generates inputs to this compliance checking function. And you can maybe parameterize it with a risk score. So you have a slightly more advanced generator. It can kind of decide what the risk level should be. And you give it a baseline, which is a neutral document, absolutely no risk. So now you can start to assert some invariants about your system, which is if you do the neutral analysis and the steady state analysis on the input, probably there's some hard invariants that you always want to be true. Maybe the person's portfolio should always have some max allowed leverage, and that's a very easy thing to formally specify. Maybe you are in various jurisdictions, and some assets are allowed and some aren't allowed. And so you can assert this hard invariant. The model should maybe never suggest an asset type that isn't allowed. And then you can make claims to moneticity, which is like, if the risk profile goes up because you made it more risky, it should probably be more, like on the risk dimension, it should be considered more risky than a neutral baseline. So now we can start to think about what properties or invariants should be true about the things that we're generating as we're sort of testing these systems. And one day the model providers might silently release an API change, and now you're actually running a new model, and you notice it starts to perform a little bit worse, and you can detect that and catch that without actually having to have like always a hard-coded golden data set. And you can also do slightly more advanced checking, which is not just, is this value true, but you can have to start to assert things about the semantics of the output. Let's say I'm building some sort of, chat bot that helps me shop, and we want it to be a little cheeky. We don't want it to be so serious. It's a fun chat bot. So we have it generate some response given some input chat history. So I give it like some production traces, chats that are actually happening, and I say generate a response. All I want to assert is that the tone of this response is always what I want it to be, right? Or I want to always assert that if I check the pricing and I check it against the ground truth, that's always true. Or I want to assert that like I'm not accidentally leaking PII that I put into the context about the user. Maybe I don't want them to know that I know certain things about them because that can be a bit awkward. And I don't want to make any illicit claims about what they're doing. So you can start to assert not just properties that are, hard about the data, price, length, these sorts of properties, but you can also start to assert semantic properties. And these end up being something that's quite powerful because models are quite difficult to predict the behavior of. And we kind of heard about shrinking earlier. Quick show of hands, how many people understand what shrinking is in the context of property-based testing? We have Zach, by the way, in the audience, who's the author of Hypothesis. If you want to learn about property testing, go use Hypothesis. Sorry, I had to give you a shout out. Hypothesis is a great library for property testing. So shrinking in property-based testing is a really great property of property testing, no pun intended, which is you take your input space and you generate some example that makes the test fail. Now, what shrinking can do is minimize that example case down into the most minimal reproducing example. That's really, really useful. If you have some giant state space that you're fuzzing, you really just want to know what the minimal thing that makes you fail is. And so if we kind of now apply the second order degree of thinking, which is, okay, I have property-based testing, that's kind of interesting. You can start to ask, like, okay, well, what does shrinking look like, right? What does it look like to kind of narrow down the semantic fuzz space, the semantic state space, and what is the minimal set of examples or the area of examples that cause my models to fail? I don't have an answer here. This is just a question. I think it's an interesting one, which is like, what is semantic shrinking? So like we have, maybe some generated cases. Maybe we can extract some clusters and then just tell you like, hey, it looks like on these class of issues, your model tends to fail more, right? And that's a useful starting baseline. It's much better than like asking you to go do the data science work of like extracting all the failures and starting to build patterns, right? And if we do believe that these language models are going to make a lot of domains economically productive, or be economically productive in a lot of domains, then we need to empower application developers with really robust tools like this one, not just empower people who have data science and machine learning backgrounds to be able to do this kind of work. And I do think that insights from, again, systems engineering and distributed systems engineering and reliability engineering in general can be brought to bear on this problem. Another technique that you'll commonly see is differential testing. So if you're building a data system and it's new, right? Maybe there's a really interesting project which is rebuilding SQLite in Rust. And what they do in their tests is they take SQLite, and whenever they implement a new method in their system, they just use SQLite as the oracle, right? So they use another model as the oracle. So when you're in a test case, what you can do is use disagreement as a pass-fail oracle. And you can kind of say, like, do these two models disagree with each other? And this is akin to differential testing. This is not a novel idea. Like, basically every company that is building reliable LLM applications actually does this in practice. And what's interesting and a little bit different than the traditional setting where these techniques come up is these techniques are useful online. So they're not just an offline thing that shows you what's happening in test. You can run them in production, and they become reliability signals. So as opposed to like, do these n versions all agree pass fail, you can now start to ask the question of, do these n versions all have some quorum, right? And this is a very obscure reliability engineering technique called n version programming, which is like often used in avionics, where you like write 4 different specs of the same software and then you like run it through. And this is very commonly done too. So a lot of LLM-based applications now, they will actually try and see what the majority of language models say about a given answer, and then they'll try to self-verify. And it's very counterintuitive that this works, because if you ask the model to do one generation and you say verify this generation, it usually gets it wrong. But if you pick 4 or 5 different models, or even the same model at various different temperature samplings, and you ask it to self-verify, it will actually get it right more often, which in my opinion is a little counterintuitive, because you'd expect the verification step to be something that is independent of the domain of where the inputs are coming from. But this also has an interesting analogy to Byzantine fault tolerance, right? We are kind of asking, like, how do we tolerate bad actors? I don't know what to do with that analogy, but it's an interesting one. So agent systems also benefit from classic safety and liveness properties. So if you have some sort of model of your system, a common way to assert things about that system is to assert invariants, again, about that property, about that system. Two very common property types in distributed systems, as you may already know, are safety and liveness. Safety is nothing bad should ever happen. It should not crash under random perturbations, unless you're building a system that's one of those, academic papers where crashing is good. And liveness is something good eventually happens, right? Some answer should be reached, some resolution should be reached, right? So an example of that is like, you could say that I always want a verification step to occur before a destructive action that my language model application takes, right? So before your language model application calls a drop table, maybe it should verify that that is the same thing to do. Or maybe you should verify that somehow the agent never contradicts something it did in the past, which is very difficult to assert statically, but is something that you can do with another language model that checks. And then for liveness, you'll probably notice this if you've ever used any of these agentic systems for coding. They sometimes get stuck in a loop where they just keep calling the same tool or keep going in circles with logic. So you can assert a property that's like, given some execution trace of the agent, can you assert that it's live? Can you assert that like it doesn't get stuck in some circular semantic loop or call the same tool a bunch of times with an input that seems basically the same, and detect these sort of properties that the system is going to actually make forward progress? There's a technique called metamorphic testing, which is kind of a flavor of property testing, in my opinion. I will just try and quickly explain it. I think it's one of the more obscure ones, which is you take some input x, right? You give it to a program which produces f of x. You then take that same input, you run it through some function called g of x, and you can then say, what is f of g of x? And if you can define some relation between f of x and f of g of x that is always true, then you know that the system is performing correctly. This kind of, if you squint, looks like data ablation in machine learning in a way. So an example here would be like if you were writing a function that implemented sine. If you did sine pi minus x, that should always be equal to x because math. So if you can define these sort of metamorphic relations over your input, that is potentially an interesting thing. And I've actually seen a handful of companies doing this. They like silently perturb the input or slightly perturb the input in order to try and assert some property. So an example here is like, imagine you have some agent that needs to root cause a bug with service A, and you give it all the logs in the cluster. So it's debugging service A. The failure case here is that you have some distracting information that leads the model to misunderstand or over-index on the wrong things, right? You just have distractors. There's a bunch of noise in the logs. So what you can do as a metamorphic relation is you can just add some more noise, right? You can just add an to the log file for an unrelated service. And if your job is to identify the root cause, it shouldn't affect the root cause. And the bias that you're exploiting here in the model is one of salience. The model will kind of latch on to an or a 500 or something that seems rather bad, but is actually unrelated. And so this is like a small relation that I saw an agent company doing, sort of a SRE-style agent company doing in order to test their system. Another one you could imagine is one of constraint stability. So imagine you have like an agent that reviews some sort of infrastructure access management policy, some role access policy. And you've kind of gone back and forth on it with like what permissions you want to inject, right? So at some time step, you said, no, I want this, and then you change your mind, and then you change your mind again. But this is all still in the context window of the model. When it makes this change or it makes this change, that rule shouldn't drop any of the other existing rules, right? This is something that is formally verifiable. And so when you add to the policy, you shouldn't weaken these other unrelated constraints. You should only affect the constraint that the user is asking you to affect. And this one I haven't actually seen done. It's purely speculative, but the reason I mentioned it is because it begs the question of how can you actually verify this, which leads me to like the last bag of techniques that I think is useful that we can borrow from people who try and build reliable, verifiable systems, which is symbolic and formal tools. So many domains for a long time have used symbolic and formal tools in order to try and verify their outputs, right? And again, I'm not going to talk about like RLVR, reinforcement learning with like verifiable rewards and all the machine learning techniques. I just want to focus on like how we can think about this from like the classical bag of techniques that we might be familiar with as systems builders and distributed systems builders. So you can kind of think about LLMs lowering the barrier to entry to author these verifiable outputs. They're normally extremely complicated to write. If you've ever written TLA+, or you've attempted to use Lean or Coq, the theorem prover, or you've tried to use Daphne, or you've tried to hand author an RDF, it's very, very complicated. And it's kind of not an easy thing for humans to do, but LLMs dramatically lower the amount of skill and information you need to have to write these sort of verifiable specifications. And so a promising technique that there's many research papers on that you can kind of go search around for is you have LLMs generate these verifiable outputs, and then you let it perform its tasks. So you kind of use the LLM as the front end in like compiler speak, and then you use like the verifier as the back end, the verification protocol as the back end. And there's policy languages, or Lean, which is like a proof assistant, or Daphne, which is a language that I think is a Microsoft research project, which is how do we actually embed verification into the language, or RDF, ways to represent structure information about the world, or even TLA+ if you're having an agent write some sort of distributed system. So this is an example from a company that is a friend called Phosphor.co. The person working on this project is Luke Vanderhart, who's actually an original contributor to Chroma. You won't find this product live, but I wanted to flag it because it's like an interesting in-the-wild example of this idea. Again, these techniques, if you've like done NLP 15 years ago, you'll be like, oh, what's old is new again, but there's some nuance. So what this product does, to some extent, is it takes legal information or legal contracts, and then it does like NLP-style entity extraction, using language models to enrich that entity extraction. So you can see here, there's two sentences, something about a borrower and a lender and a bank. And we can extract the entities, borrower, lender, bank, and you can see the entities that are extracted. And it's also able to sort of coalesce different references to entities that are different in name or different in semantic together. And then what we can do is start to extract these propositions or these relations between these entities. And once you have these in a system like RDF or OWL, you can start to ask verifiable questions about the data. So you can always say, like, who does the borrower owe money? And it won't hallucinate. You know it'll give you a correct answer. And I think these sorts of techniques are really important for domains where failure is not an option. You can't be wrong if you're going to give an answer on a legal case, unless you don't want to make money. So I think these sorts of techniques are incredibly useful if you're operating in domains with a high degree or need for accuracy and also for reliability, which is why I think they're fruitful. So the question I'll leave you with is, reliability doesn't really mean that you're making the model perfect. It's how do you make a system that deals with these non-deterministic or imperfect parts and engineer something that is quite reliable. And I want to know what other techniques we can bring to this domain. This is a very rich and deep field. There's a lot of history. And I think that if we start to go back and you start to dig into the work that people were doing, I think you can start to resurrect some of that and make it useful. So if you know of any or you have an idea, please come talk to me. I'd love to learn, and we're hiring at Chroma. Thank you.